So up to now, we have only looked at internal changes within a molecule. For example, we looked at ring flip and bond rotations, but going forward, we will be seeing chemical reactions, changes that occur between molecules. And actually, this will be the large focus of the remainder of the semester and even going to second semester of organic chemistry. So this lecture will be very important as it will serve the foundation that you will need in order to be successful in subsequent material. So what are we talking about? In this video, we will be looking at nucleophiles and electrophiles, and then looking at patterns of arrow pushing to described mechanisms. So who are the major players when we are talking about chemical reactions? And the answer are nucleophiles and electrophiles. So most of the reactions in organic chemistry is what is known as ionic or polar reactions. Both of these words indicate there is a disparity in the distribution of electron density. And in fact, we will often see ions as either reactants, products, or intermediates. So again, ionic reactions will focus on two main players, the nucleophile and the electrophile. So for example, we have here this molecule bromomethane. Taking a look at this molecule, where do you think the electron density will be concentrated? Thinking back about electronegativity, we notice that bromine, a halogen, is very electronegative. So it would pull electrons toward itself and away from the carbon center. So that carbon is partially positive, and that bromine is partially negative. Due to this carbon in the center is lacking electrons. Because of this lack of electrons, it is attracted to electrons. It wants and loves, quote unquote, loves electrons. So it will be called an electrophile. And that carbon center will be known as the electrophilic center. On the other hand, this chlorine ion is full of electrons, so much so that it has a formal charge of -1. Because it is full of electrons, which is negative, it is attracted to something that is positive. And what is more positive than the nucleus of an atom where protons are, right? It is called a nucleophile, or it could be also called as nucleophilic center or nucleophilic site. So let's go ahead and take a closer look at both of these players, starting with our nucleophile. And in this class, you will see nucleophiles often abbreviated as NU or NUC. Right, so first off, let's connect this to a term we already know. A nucleophile is also a Lewis base. Because in a chemical reaction, a nucleophile will donate its electron density towards the electrophile, much like a Lewis base. Oftentimes, these electrons come from lone pairs or from a pi bond. Some examples of nucleophiles are below. This methanol is a nucleophile. Do you see where the nucleophilic site is? That's right, the lone pairs on that oxygen is the nucleophilic site. What about this alkoxide, this alcohol that has been deprotonated? Yes, again, it is the lone pairs on that oxygen, that negatively charged oxygen. In fact, this species is more nucleophilic than the neutral counterpart. So this negative charge species is even more full of electrons because of that negative charge than its counterpart, which is neutral. Now note, this methyl chloride is not an example of a nucleophile. Those lone pairs on the chlorine will not serve as a good nucleophilic center because the chlorine is very electronegative. If it were to donate its electron away, it would be a positively charged chlorine, a formal charge of +1. Because of its high electronegativity, chlorine will not be very stable. Because of that instability, this molecule is not a nucleophile. And those lone pairs are not nucleophilic centers. On the flip side, do you see a nucleophilic center in this molecule? Just because we do not see the lone pair doesn't mean we do not have a nucleophile. Remember, a nucleophile possesses a high electron density. And what do we learn about the pi bond? It is a region of high electron density. So yes, pi bonds will be a nucleophilic site. Now, a third thing I want to talk about concerning nucleophiles is this idea of polarizability. And there are many factors contributing to nucleophilicity, but perhaps the most important is this idea of polarizability. It is basically the ability of an atom to unevenly distribute its electron to accentuate the electron density. In other words, in making one side of an atom more electron dense than another, and therefore more polarized. In essence, the more easily you can redistribute the electrons around an atom to be in one specific site, the more polarized it is, making it a better nucleophile. So what determines polarizability? Remember back in your general chemistry days, which atoms has less control of its electrons? If its electrons close to it or if the electrons are far away from it, right? So if the electrons are farther away, it is less in control. So the pattern is the larger the atom, the more polarizable it is. So for example, can you rank the nucleophilicity of the following species? Let's take a look at the first two species here. Notice that they have the same nucleophilic site, the lone pairs on the oxygen. However, our hydroxide should be more nucleophilic because it has a full-on negative charge. And now let's bring the last molecule in here. It is also a full-on negative charge, so we know it's going to be also higher than the water molecule. So how does it compare to our hydroxide? Because the nucleophilic site in sulfide is on that sulfur, it is going to be more nucleophilic than when it is on that oxygen because sulfur is a larger atom than oxygen. It therefore is more polarizable and more nucleophilic. Next, let's take a deeper look at electrophiles, sometimes abbreviated with the letter E. Alright, so again, the first thing you want to notice, if there was a Lewis base, then there has to be a Lewis acid. It turns out electrophiles will act as your Lewis acid. It will be accepting electrons in a chemical reaction. Electrophiles are often found in molecules where there is a carbon connected to a very electronegative atom. For example, in this chlorobutane. Notice that there is that chlorine connected at the end to a carbon. And that chlorine has a very strong dipole pulling electron density towards itself and away from the carbon. This inductive effect will create an electrophilic center at that carbon. Another common electrophile is a carbocation. We've seen carbocations before. Remember, in a carbocation, there is an empty p orbital, so that carbon is not yet a full octet. Because of this, it wants more electrons, so it will be highly attracted to nucleophiles. So again, whether you are full-on positive charge or a partial positive charge, you will create an electrophilic center. So if you can recognize a nucleophile and an electrophile, you will be able to understand more easily the reactions that we will be looking at going forward. So let's go ahead and do some practice to identify nucleophilic and electrophilic sites. Is this a nucleophile or an electrophile? Hopefully you noticed that there's a lithium here, and the lithium is a cation. So you can literally write this where that lithium has a positive charge. Therefore, on the other end of that bond, the carbon would have a full-on negative charge. Because of that, those lone pairs will be considered the nucleophilic center. What about this molecule? Hopefully you recognize that there is this carbonyl. And in a carbonyl, carbon-oxygen double bond is quite polar. It pulls the electrons toward oxygen more, leaving the carbon in the bottom lacking electrons. So you will consider that the electrophilic center. You can kind of see it more readily if you drew in the resonance structure for this molecule, where the double bond breaks and dumps the electron on the more electronegative atom, the oxygen. So in this resonance structure, you can see that the carbon is indeed the electrophilic center. You can also see that the oxygen has a high density of electrons. So sometimes that site is considered the nucleophilic site. So it will depend. If you are reacting this with another nucleophile, then the electrophilic site of this molecule is important. But if you are reacting this molecule with a strong electrophile, then the nucleophilic site will be of interest. How about this molecule? What do we recognize? Hopefully you see that this double bond is indeed a nucleophile. Let's do one more. So in this molecule, you will see that within this one molecule, there could be many nucleophilic and many electrophilic sites. Can you identify them all? Hopefully you can see that the oxygen and the nitrogen will be your nucleophilic site. It might be more obvious if you drew in those lone pairs. And there is this one electrophilic site because it is next to that very electronegative atom chlorine. So now that we have recognized the players, let's see how they will react with one another. And so mechanisms are what we use to show how reactions takes place, how electrons moves as bonds are breaking and bonds are forming. And to show that, we use what is known as curved arrows. And in the previous videos, we've already laid the foundation for some fundamentals of arrow pushing. And in this section, we will apply that into the context of mechanism. So when you're drawing a mechanism, you're showing how a molecule changes as it reacts to another molecule. And luckily for us, in this semester, and a large part of second semester organic chemistry, there's only 4 patterns you need to remember. A vast majority of mechanistic steps will involve one of these arrow pushing patterns. They are nucleophilic attack, loss of leaving group, proton transfer, and rearrangement. We'll go ahead and take a look at each of these steps in detail. So the first one here is nucleophilic attack. I like to abbreviate it as NA. So in a nucleophilic attack, you have your nucleophile attacking your electrophile. It's a very archaic term to use attack, but essentially your nucleophile is donating its electrons into the electrophile. So we draw that electron donation with this curved arrow starting from the lone pair on the nucleophile and ending on the electrophilic center, that carbon, that carbocation. So with that single arrow, we form a new species and we have formed a new carbon-chlorine bond. Let's see another example of nucleophilic attack. In this example, first, can you identify your nucleophile and electrophile? Again, you have in this your nucleophile who will donate its electron, its lone pair of electrons, towards the electrophilic center, which is the carbon of that carbonyl. In this example, a second arrow is needed. And the reason for that is the new carbon-oxygen that is formed will make the carbon exceed the octet. It now has 5 bonds, which is 10 electrons. It cannot accommodate that. So to alleviate that, we need to introduce a second arrow into this mechanism. Because that carbon cannot form a 5th bond, at the same time, it will break one of its carbon-oxygen bonds and dumping those electrons onto the oxygen, giving this species. Notice that the oxygen-carbon bond is formed along with this lone pair. Each curved arrow will result in the change of the electrons somehow. In this case, the first arrow made a lone pair become a bonding pair, and in the second arrow, a bonding pair becomes a lone pair. Our second pattern is the pattern of the loss of a leaving group. I like to abbreviate that as LLG. So we have here this molecule where there is a good leaving group. Now, I just used a term that we don't understand yet. A good leaving group is a concept that we will cover in our next video. But for now, we're just looking at the patterns. Okay, so bromine is a good leaving group. So as it leaves, it will take electrons with it. And so this is the pattern for the loss of a leaving group. As a result of this arrow pushing, you will have 2 species. You will have a carbocation and this bromide ion. In this example, the arrow starts from a carbon-bromine bond and ends on a bromine atom. So the electrons from a carbon-bromine bond is now the electron on this bromine ion. Okay, let's see another example. Notice that in this case, there's two arrows. In the first, we have the lone pair from the oxygen kicking itself in, therefore forming a second bond to that carbon. Now that carbon has 5 bonds or 10 electrons exceeding the octet. Because of that, it can't accommodate the bond to bromine anymore, so therefore it kicks it out, which is why we have that second arrow in there. Again, let's highlight what is formed. So in the first arrow, a lone pair is transformed into a bonding pair. And the second arrow, a bonding pair is transformed into a lone pair. So we have here an example of a loss of leaving group pattern involving 2 arrows. Our third pattern is proton transfer, often abbreviated as PT in my class. It looks very much like a nucleophilic attack. So we have here the acid and the base. Again, the base would be your nucleophile and your acid would be your electrophile. So in a proton transfer step, the lone pair from the base will attack the proton. Now, in that first arrow, notice that you are making a bond to hydrogen, right? When the arrow from the lone pair from your base is drawn towards a proton, it means it's going to share a bond with it. What is not right with this molecule? So that proton, which is a hydrogen, right, cannot accommodate more than 1 bond at a time. It now has 2 bonds to it. So to accommodate this reaction, it must break its bond with the original oxygen. Right? So to signify that, we draw an arrow from that OH bond and dumping the electrons onto the oxygen itself. And so when we do that, we now have 2 molecules looking like this. So as you have seen, we need 2 arrows for this proton transfer to work. And we draw them at the same time. So our first arrow is the abstraction arrow, and our second arrow is the breaking of the original acid bond. So let's go back to our project over here. And so remember that this has a formal positive charge of 1 on the oxygen. And so again, let's highlight what bond is formed when we do this proton transfer. That is our new bond. And that is our new lone pair. Let's take a look at another example where you can have multiple arrows. Okay, so in this one, the arrow pushing looks like this. The first step is attack of the proton, followed by the breaking of that acidic proton bond. But in this case, you can't just leave it as that. You would need to do a third arrow pushing. And as a result of that, you would get this product. Again, let's highlight what's being formed. First off, in that first arrow, we form a bond with that acidic proton. In the second arrow, we form a double bond between the carbon-carbon. And in the third arrow, we formed a lone pair. Again, let's break down the steps. If we did this proton transfer like we see in the previous case with 2 arrows, we will have something that looks like this, where you have this negatively charged carbon on this molecule and your water product. Now you can imagine that this molecule can have a resonance structure because it does have a lone pair that is allylic to a pi bond. So you essentially have this molecule that is the most stable species at the end, but as a resonance structure. So to represent this, we just do it all at once in a concerted fashion in this one single arrow pushing. All right, our last pattern here is rearrangement, and I abbreviate that as RAR, and this often involves a carbocation. So let's first discuss the stability of carbocations. Let's take a look at the simple case of a carbocation, a 2-carbon carbocation. Let's re-represent this carbocation with its atomic orbitals. So notice in this carbocation, there is adjacent to it this methyl group. And it turns out this methyl group can rotate in a way that one of the carbon-hydrogen bond is perfectly aligned with this empty p orbital. And so when this happens, there is this side-to-side overlap, almost like the electrons between that carbon-hydrogen bond is donating itself into this empty p orbital this electron-lacking carbocation, therefore stabilizing it. This effect is known as hyperconjugation. So now this only can work if a carbocation has an adjacent carbon next to it, because that carbon will have more bonds connected to it, whether it be to this hydrogen, as in this example, or to another carbon. That also will work. What would you say if instead of this hydrogen here, you have another methyl group? Would this carbocation be more stabilized? It would, right? Because it can again have a carbon-hydrogen bond that can donate itself into that carbocation, stabilizing it. So it turns out there's a hierarchy of stabilization between different types of carbocation. So if you are a simple methyl group, there is no hyperconjugation, you are very unstable. With increasing amount of alkyl substitution, you will have more and more hyperconjugation and therefore more stabilization. Now let me add some more complexity to this pattern. Is when you have a secondary carbocation, it has the same stability as an allylic carbocation or benzylic carbocation. Remember that this is not hyperconjugation, but rather the effect of resonance. So carbocations can also be stabilized by adjacent pi systems. And then if you add these two effects together, you can have something more stabilizing than a tertiary. So for example, if you have a substituted allylic position, you not only have the resonance structure from the pi bond, but also having the hyperconjugation effect from it being more substituted. So in fact, that molecule itself is even more stable than your tertiary carbocation. Okay, but why do we need to know about the stability of carbocation? So it turns out in this pattern of arrow pushing, a hydrogen or a methyl will shift in order to create a more stable carbocation. Let's say you have this molecule, which is a secondary carbocation. Now notice that adjacent to it, there is this hydrogen. You can imagine that this hydrogen is hyperconjugating into this empty p orbital, right? Now, if it does it so extremely that it not only just donates into that orbital, but completely move into those orbitals, you would form a new bond. And therefore, we can represent that with this curved arrow. Remember, it already had one original hydrogen. So now this is now your new carbocation. Notice that this is a tertiary carbocation. So whenever you can transform yourself to become a more stable carbocation, you will always do that via a hydride shift, which is what this is, or a methyl shift. This is what is known as rearrangement. Let's highlight the changes that this curved arrow makes. So in this case, a bonding pair of electron shifts over to still be another bonding pair of electron. So that pattern is a little bit different from the ones we've seen in the previous three. So again, this is called a 1,2 hydride shift because that hydrogen moved from a position of carbon 1 to carbon 2, an adjacent carbon. Again, this can happen with a methyl shift. For example, in this molecule, instead of a hydrogen shifting, any of those methyl groups can do a shift into the carbocation. Again, the driving force behind this is that you started out as a secondary carbocation and ended up with a tertiary carbocation, a much more stable carbocation. So again, let's highlight what bonds are formed with that curved arrow. With that curved arrow, you have formed a new carbon-carbon bond. That is called a 1,2 methyl shift. So that rounds up our fourth pattern, but I want to go a little bit more detail and take a look at more examples of carbocation rearrangements. Alright, let's say you have this molecule. Can you predict the carbocation rearrangement that will occur? Notice right now you have a secondary carbocation. So you want to be able to shift in a way to give you your tertiary carbocation. Hopefully you saw that there was this hydrogen adjacent and that hydrogen can do a hydride shift into that carbocation, giving you your tertiary carbocation. Now let's say you didn't see that hydrogen and instead you drew a methyl shift instead. Would this be okay? This would not, right? Because you did a methyl shift that only gave you another secondary carbocation. Since you did not gain anything, this reaction has no driving force, so it will not happen. So in fact, this is the route you want to take. All right, how about this last example here? Notice that it is already a tertiary carbocation, so the only way it can improve from that is that it is going to be a substituted allylic carbocation. And so hopefully we see that there's this hydrogen that can do a hydride shift into that carbocation, giving this our new carbocation, which is tertiary but also allylic to a pi bond. All right, let's do some practice here. What about this molecule? This is a secondary carbocation. Can we make it tertiary? Yes, we can do a 1,2 hydride shift. Very good. How about this molecule? No, you can't, right? It's already a tertiary carbocation. There's nothing more we can do to stabilize it. What about this tertiary molecule? Can we stabilize it? Yes, we can. We can do a methyl shift. Because when we do that methyl shift, we have a substituted carbocation that is allylic to a pi bond. Maybe one more. How about this carbocation? It is secondary carbocation. Can you do anything that will help? Indeed, you can do a hydride shift. And with this hydride shift, you get a secondary carbocation again, but it is now benzylic, right? So it also has resonance. So that will be the driving force for this stabilization. At this point, I want to also highlight some common mistakes that novice learners make when they first drawing mechanisms. I just want to remind you that when you draw curved arrows, you have to be very precise because where the arrows end and start has a very unique significance. For example, curved arrows needs to start on a pair of electrons, whether that be a bonding pair or a lone pair. So for example, in this mechanism, that nucleophile is attacking that electrophilic center and kicking out this chlorine as a leaving group. This is a proper depiction where the arrow starts on a pair of electrons, whether that be this lone pair of electron or this bonding pair of electron. So don't draw this as your second arrow, starting from the carbon and not the bond itself, or draw the chlorine leaving like this, because again, you want to indicate that that carbon-chlorine bond is breaking. And the second rule here is that the curved arrows must end with formations of a bond or a lone pair that I've been emphasizing as we go through the patterns. So for example, in this case, our first arrow is an arrow that forms a bond, and our second arrow is an arrow that forms the lone pair. So stick with arrows that follow this rule. And the third common mistake I want to alert you to is to always follow the rule that you do not exceed the octet for second row elements. So for example, if we did an arrow pushing like this, you would create a species with a carbon with 10 electrons. Okay, so just follow these rules and you should be fine. Now before we end today, I just want to touch base quickly on the reaction arrows we've been using. Sometimes you see me using a one-directional arrow and others a reversible arrow, a bidirectional arrow. Well, the first one symbolizes an irreversible reaction, so it's going in one direction only. And the second is a reversible reaction where the reaction can go forward or backwards. So how do you decide when to use what? So here are some general guidelines that hopefully you will find useful. And we will discuss this per pattern of reactions. Let's go ahead and take on the first example for nucleophilic attack. When you do a nucleophilic attack and your nucleophile when attached is a good leaving group, it will be a reversible reaction. Because if it is a good leaving group, as the word suggests, it can leave this molecule forming your reactants again. We will take a closer look at leaving groups in our next video, so you don't have to master this concept just yet. So don't worry if you don't know how to recognize leaving groups just yet. So for example, in this case, only the forward reaction will occur because you have a bad leaving group. So we will use the irreversible reaction arrow. In our second example of the loss of leaving group, we will often use the reversible arrow because oftentimes the leaving group is also a good nucleophile. So it can go back and attack that electrophilic center to form your reactants. For the case of proton transfers, it's a little bit trickier, and so it depends on the case. In this case here, we will use an irreversible arrow. And this is because if we look at the acids on both sides of this equilibrium, we will have a difference of pKa of 34. This means that at equilibrium, you have 10 to the power of 34 butane molecules to one water molecule. It essentially goes in one direction. So we will use this irreversible reaction arrow. Contrast this to reaction of tert butoxide with water. The pKa difference here is much less. So because of this, there will be a substantial amount of reactants at the completion of this reaction. So we will use the reversible reaction arrow for this reaction. So what is the cutoff, you say? A good general rule is that if you have a difference in pKa of more than 10, you will use the irreversible reaction. And if it's less than 10, you will tend to use the reversible reaction arrow. And lastly, the rearrangements. So because the driving force is so favorable to go towards the more stable carbocation, when we draw the hydride or methyl shift, we will use the irreversible reaction arrow. So that ends our unit and introduction to mechanisms.